Okay, let's take a look at this worksheet for section 1.6. And notice that the objectives of this section are to solve polynomial equations by factoring, solve radical equations, solve equations with rational exponents, solve equations that are quadratic in form, solve equations involving absolute value, and to solve problems modeled by equations. So those are all the things that are covered in this section. So a polynomial equation results by setting two polynomials equal to each other. The equation is in general form if one side is 0 and the polynomial on the other side is in descending powers of the variable. The degree of a polynomial equation is the same as the highest degree of any term in the equation. So solving a polynomial equation by factoring involves moving all non-zero terms to one side and obtain 0 on the other side. So that's step 1 of solving a polynomial equation by factoring. Step 2 is to actually factor. So you're going to factor the side of the equation that has the polynomial. Step 3 is to set each factor equal to 0. Step 4 is to solve the resulting equations from step 3. And step 5 is to check the solutions in the original equation. So remember, you don't want to go back to some equation that you've changed or altered, but you want to check those solutions in that original equation. So that's our 5-step process of solving a polynomial equation by factoring. So if we want to solve this equation by factoring, we want to do step 1, which is to get all non-zero terms on one side of the equation and 0 on the other side. So I'm going to add 8y squared to both sides of the equation. I'm going to subtract y from both sides of the equation. And that will give me 4y cubed plus 8y squared minus y minus 2 on my left side and 0 on the right side. So I added 8y squared and subtracted y from both sides of the equation to obtain this. And now I'm going to factor. This is a case where I'm going to factor by grouping. So I'm going to group the first two terms together and factor out their GCF, which is 4y squared. That's the largest expression that divides evenly into both terms. And then I check that if I multiply this greatest common factor, GCF, by each of these terms in parentheses, do I get the terms back, the first two terms back, from the original equation. So 4y squared times y is 4y cubed. 4y squared times 2 is 8y squared. Now, if this process is going to work, then there's got to be a GCF that I can factor out of the last two terms that also multiplies by y plus 2. And it turns out that GCF is a minus 1. So if I multiply minus 1 times y, I get minus y, and minus 1 times 2 does give me minus 2. And I'm going to put these GCFs in red. And so I've got this common factor of y plus 2. So I'm just going backwards with the distributive property here. Y plus 2 is my common factor. In first position, y plus 2 is multiplied by 4y squared. And in second position, y plus 2 is multiplied by minus 1. So that gives me my factored form. And notice I can now solve this by taking each of these factors that has the variable in it and setting them equal to 0. So either y plus 2 is 0 or 4y squared minus 1 is 0. So y is negative 2 or four y squared is 1. So here I've added 1 to both sides. So that means y squared is 1/4. And that would mean y is plus or minus the square root of 1/4, which is plus or minus 1/2. So my solution set consists of these three solutions: negative 2, negative 1/2, and 1/2. So that would be my solution set. All right, so I can solve polynomial equations by factoring. We also in this section talk about radical equations. A radical equation is an equation in which the variable occurs in a square root, cube root, or any higher root. We solve radical equations with nth roots by raising both sides of the equation to the nth power. So these are actually inverse operations. If I have an nth root and I need to get rid of it, I use an nth power. Just like if I've added something and I want to undo that, I subtract what I've added. This is similar to that. To undo an nth root involves using an nth power. So here's my process for solving radical equations containing nth roots. If necessary, arrange terms so that one radical is isolated on one side of the equation. And this says one radical because sometimes the equation has more than one radical, and you're only able to isolate one of the radicals in some cases, not both of them. Raise both sides of the equation to the nth power to eliminate the isolated nth root. Solve the resulting equation. If this equation still contains radicals, repeat steps 1 and 2. Check all proposed solutions in the original equation. In this case, the check is required if you've raised both sides of the equation to an even power. You're going to have to check the proposed solutions because some of them may actually not make the original equation true. So in general, when you're doing this type of problem, the check is part of the work. All right, so let's look at applying this process to exercise 13 from this section. So I want to solve this. The radical is already isolated on one side of the equals. So my next step, I see I'm dealing with a square root. My next step is to square both sides of the equation. So when I square the square root of x plus 3, I simply get x plus 3. Here when I square, I have to keep in mind that this means x minus 3 times x minus 3. So I have to keep that in mind. So first time first gives me x squared. Outside time outside gives me minus 3x. But that's also what I get when I do inside time inside. So minus 3x is minus 6x. And minus 3 times minus 3 is plus 9. So this is what results, and I don't have any radicals remaining, so I'm ready to get this in standard form by subtracting x from both sides of the equation and by subtracting 3 from both sides of the equation. So I have 0 now on the left and x squared minus 7x plus 6 on the right. And this can be solved by factoring. The factors of this are x minus 6 times x minus 1. And if you need to check to make sure that's right, do that on scratch paper. If you need to do calculations to make sure that this is right, do that on scratch paper. So if you're taking an exam, you would be doing that on the back of one of the sheets. So x minus 6 is 0, which means x equals 6. Or x minus 1 is 0, which means x equals 1. And so what I do with this is I check these by putting them into the original equation. So is the square root of 6 plus 3 equal to 6 minus 3? Is the square root of 9 equal to 3? It is. So we know that x equals 6 then is really one of my solutions. Is the square root of 1 plus 3 equal to 1 minus 3? Is the square root of 4 equal to minus 2? And the answer is no. When you are applying radicals, that's called a principal square root. And the principal square root, a lot of time we just say square root for short, but the principal square root of 4 is a positive 2, not a negative 2. So this is an extraneous solution that I need to discard. So x equal 1 solves this equation I got after raising both sides to the second power, but it doesn't solve my original equation. So you can see why the check is required on these types of problems. Okay, so my solution set consists only of the 6. 6 was the only value of x that was a possible solution that made the original equation true. We also want to look at equations that involve rational exponents. So x to the m over n equals the nth root of x to the mth. So a radical equation with rational exponents can be solved by isolating the expression with the rational exponent and raising both sides of the equation to a power that is the reciprocal of the rational exponents. Okay, so here's an example of this type of problem. I've got a polynomial raised to the 3/4 minus 2 equals 6. Now we said the first thing I need to do is isolate the expression with the rational exponent. So my expression is not isolated, but it will be if I add a 2 to both sides of the equation. So I now have x squared minus x minus 4 to the 3/4 equals 8. And so the process is for me to, now that I have the expression with the rational exponent isolated, now the process involves me applying the reciprocal of this rational power to both sides of the equation. So the reciprocal of 3/4 is 4/3. So I raise both sides of the equation to the 4/3 power. And the rules of exponents say if I'm taking some expression, raising it to some power, let's call that power m, and then I raise that exponential expression to the nth power, I multiply those powers. So when I raise this expression to the 3/4 to the 4/3, 3/4 times 4/3 is the product that is m over n, m times n over here. So m times n is 3/4 times 1/3. Well, that's just the first power. So let me just show that. So 3/4 is getting multiplied by 4/3. Then I have 8 to the 4/3. And so this is just to the first power. So x squared minus x minus 4 is raised to the first power, and the first power can be left unwritten. A 4/3 power means to take the cube root of 8, and whatever that is, raise it to the 4th. I could also look at that as taking the cube root of 8 to the 4th. So which one do? I do whichever one is easiest, and it's easiest to do what I wrote first. It's easiest to take the cube root of 8, which is 2, and then raise that to the 4th power. And that will give me the same result as raising 8 to the 4th and then taking the cube root of whatever that is. So 2 to the 4th is 16. So x squared minus x minus 4 equals 16. And I'm going to subtract 16 from both sides to get this in standard form. So x squared minus x minus 20 is 0. So I can factor that. The factors are x minus 5 times x plus 4. So x minus 5 is 0, or x plus 4 is 0. It's possible both of these might work. It's possible only one of them might work. It's possible that neither one of them works. So it just depends on the nature of the problem. All right, so I've got two proposed solutions, and those need to be substituted into the original equation. And remember, that was x squared minus x minus 4 to the 3/4 minus 2 equals 6. So let's check x equal 5. So 5 squared is 25, minus 5 minus x is minus 5, minus 4. That gets raised to the 3/4. I subtract 2, and that needs to equal 6. Okay, I wrote that a little smaller. So this is 20 minus 4, 16. This is 16 to the 3/4. Minus 2 equals 6. So that means I'm taking the 4th root of 16 and then cubing it. But the 4th root of 16 is 2. 2 cubed is 8. So this works. Okay, so that works, which means x equal 5 is a solution. Let's check this negative 4. When I square negative 4, I get 16. 16 minus minus negative 4 is 16 plus 4, minus 4 to the 3/4, minus 2 needs to equal 6. So obviously I get the exact same thing when x is negative 4, because I get 16 to the 3/4 minus 2 equals 6. And we already saw that that is going to give us 8 minus 2. The 4th root of 16 is 2, And when I cube 2, I get 8. Okay, so this works as well. So in this particular case, I get 2 solutions. So my solution set consists not only of the 5, but also of the -4. So sometimes people think you toss a possible solution out because it's negative. No, you toss a possible solution out because it doesn't solve your original equation. It is possible that a negative value might solve your original equation. Okay, another thing found in this section is this solving equations that are quadratic in form. So an equation that is quadratic in form is one that can be expressed as a quadratic equation using an appropriate substitution. So let's look at exercise 1.6.58, where we're told to solve this by making an appropriate substitution. So this is actually not quadratic. If I square x squared minus 2x, the term of highest degree is going to have degree 4. So this is really a 4th degree equation. I'm going to use the substitution where I let the letter u equal x squared minus 2x. So I'm going to go back, and wherever I see x squared minus 2x, I'm going to write a u. So I see it right here in first position, and I see it in the second position. So notice I was squaring x squared minus 2x here. So this is u squared. Here I was subtracting 11 times x squared minus 2x. So that's minus 11u plus 24 equals 0. So notice wherever I had x squared minus 2x, I replaced that with a u. And this factors into u minus 8 times u minus 3 equals 0. So either u minus 8 is 0, which means u equals 8, or u minus 3 is 0, which means u equal to 3. Okay, so, but what is u? Remember, u is x squared minus 2x. So this is x squared minus 2x equals 8. And if I put that in standard form, x squared minus 2x minus 8 is 0. So x minus 4, this factors into x minus 4 times x plus 2. So either x minus 4 is 0, or x plus 2 is 0. So x is 4. I get 2 solutions from this, and that is x is 4 or x is minus 2. I'm going to move this over a little bit so I have more room. Okay, so u equals 3. So in other words, when I solve these types of equations, I want to make sure I go back to the original variable and I don't wind up talking about what u equals, the letter. I can use any letter I want in my substitution as long as it's not the original letter in the original equation. So if my equation originally involved x, I want to make sure that at the end I'm saying what x equals, not what my new letter that I use for the substitution equals. So x squared minus 2x then will equal 3 since u equals 3. Wherever we see a u, we are now going to replace that with x squared minus 2x. If I subtract 3 from both sides, I get x squared minus 2x minus 3 equals 0. And this can be solved by factoring. the polynomial into x minus 3 times x plus 1. So either x minus 3 is 0 or x plus 1 is 0. So x is 3 or x is negative 1. And so this is my solution. And notice we said this was a fourth degree polynomial, which can have at most 4 solutions. So my solution set is the set containing negative 2, negative 1, 3, and 4. And if you substitute those back into the original equation, they make that original equation true. We also want to look at equations involving absolute value. So the absolute value of x describes the distance of x from 0 on the number line. To solve an absolute value equation, we rewrite the absolute value equation without absolute value bars in an equivalent form. So absolute value is really, in most cases, a compound statement. So here's what we're going to use. If C is a positive real number and U represents an algebraic expression, then the absolute value of U equal to C is equivalent to U equals C or U equal negative C. So that's what we're going to use when we try to solve problem or exercise 66. The absolute value of 2x minus 3 equal 11 means that 2x minus 3 equals 11 or 2x minus 3 equals negative 11. So this rule that we just looked at allows me to rewrite this equivalently without absolute values. So I cannot start to solve this until I remove the absolute value bars by rewriting it in an equivalent form. So I'm going to add 3 to both sides for both of these equations. And for the left equation, that gives me 2x equals 14, which means x equals 7. Here it gives me 2x equals negative 8. If I divide both sides by 2, I get x equals negative 4. So those are my solutions. So my solution set is the set containing negative 4 and 7. Only those two values of x will make this true. If x is negative 4, if I were to substitute this into here, I would get the absolute value of negative 11. And of course, the absolute value says how far negative 11 is from 0. It's 11 units from 0. So the absolute value of negative 11 is 11. When I replace x with 7, I get the absolute value of positive 11, which is also 11. So there are two numbers that are 11 units from 0, 11 and negative 11. Okay, so that's how I solve an absolute value equation.